everyone. So we're going to do a quick little orbit activity. I'll give you a rundown of how to use this simulation. It can be a little bit tricky to get used to. So if you head over to the simulation, FET Gravity and Orbits, you'll be given an option of using the model or the scale version. Let's use the model version. So just move something out of the way. Okay. So if I hit clear here, let me just reset this. I was using it earlier. A couple things you need to do each time you use this simulation. You have to check off force of gravity, check off velocity, check off path, and check off grid. When you reset it, it's going to reset those. So just make sure you fix that each time. This does take a little bit of getting used to, but overall, it's a really good simulation once you learn how to use it. So if we hit play, we'll see that's the Earth going around the sun. The orbit is nearly circular. We're going to assume for our purposes here that all orbits are circular. In reality, no orbits are perfectly circular, but a lot of them are pretty close. Like Earth's orbit, you can see here, it's just fairly accurate. It's not a perfect circle. You can kind of tell by the grid lines, but it's pretty darn close. All right, and if you look at the period, it should finish in about 365 days, which we see right about there. Okay. So, what are some things you could do with this simulation? So, I would not recommend doing any changes without pausing the simulation first. So, the first thing I can do with this simulation is I can increase the mass of the planet. So, if I can make the Earth twice as massive. You'll see how that affects the force of gravity and how it affects or doesn't affect its orbit. If I put that back, I could change the mass of the sun. Notice it makes the sun bigger, but it does not change the center to center distance between the Earth and the sun. So R is not changing. If I hit play, this actually drastically changes the Earth's orbit. Okay, we'll see if the Earth gets some sort of an elliptical orbit. Now, another thing I can change here is I can change the speed. So if I pause it, let's say at this point here, and I say, let me give it more velocity, I can grab that velocity vector and make it longer. Change the direction too. I'll just make it a little longer, and that will affect the orbit. Did we lose it? It might come back. I think we lost it. Okay, you can return objects. And I'm just going to reset the simulation because it started to get a little bit messy there. All right, so that's the nuts and bolts of how this works. Now, let me just show you a couple things that I just want to point out. One thing that I was talking about yesterday was why velocity is required to keep something in orbit. So I just want to show you some specific cases here. So we like to think of gravity always acting downward. So I'll kind of use that for this part here. So if I take the velocity away, just take it away completely. So the velocity is basically zero, and I hit start. Look what happens. The Earth goes right into the sun. So the Earth needs velocity to stay in orbit, to keep missing the sun. And I think this simulation does a pretty good job of showing that idea. So let's go back to that top part there. If I hit pause right at the top, it doesn't really matter where you do this, but I just like to do it at the top. If I increase the velocity, not only am I not going to hit the sun, but now I'm going to miss, okay, because the sun's gravity isn't enough to pull me down, okay, to help me fall. If I make it a little bit smaller, make the velocity pretty small, it's going faster, but it looks like I might still hit the sun, and we do. There's no way to make the Earth reappear here, I don't think, so I have to just reset it. So to get a perfectly circular orbit, you have to have pretty spot on parameters, I say, pretty exact parameters. That's why all orbits are somewhat elliptical, and some are very elliptical. Okay. Like you can actually move the sun, but I wouldn't recommend doing that in the simulation. But if I were to just like move this closer, I'm probably going to get some sort of an elliptical orbit. It'll still orbit, but it'll be much more of an ellipse. Notice how the force of gravity gets much larger when it's closer and much smaller when it's farther away, which we kind of expect. You could also notice how the velocity vector changes slightly when it gets smaller when it gets closer rather, versus when it's far away. Okay, now that should kind of make sense to us because we learned last class that as radius gets smaller, as you're closer to the planet, you have to go faster. All right, we're going to explore that though, piece by piece today though. So the first part of this activity is pretty easy. You don't even need to run the simulation. The first part of this activity is to look at how the mass of the sun and the earth affect the force of gravity on each of them, and how the distance affects between them affects the force of gravity on each of them. So that's really easy. You could just change the mass of the sun, change the earth, the sun. You could change the distances. The force of gravity is that blue arrow. So just make comments about how moving those things and changing their masses affects the force of gravity, bigger, smaller, whatever. And then make a comment about Newton's third law. So that part's pretty easy. This part is where I don't want to say it gets tricky here, but one thing I want you to emphasize is that I want you to look at how does mass affect orbital velocity. Now, in order to figure that out, you need to keep the orbital radius constant. Okay, so you need to make a nice circle. So let's see how we can possibly do that. So this took me a couple tries, but overall it really wasn't that bad once I did it a couple of times. All right, just give me 1 second. I just want to pause this real quick. All right, we're back recording. Sorry about that. So I want to look at how velocity will affect it. Well, if I make the velocity smaller, look what happens. I can't really get a circular orbit. It starts falling in towards the sun because it's not going fast enough to miss the sun as it falls towards it. Right? That's what velocity or orbits are all about. You need enough velocity to miss the planet before you hit it, like a satellite around the Earth. So let's go back here. Again, we'll go to the part where we're at the top of the orbit. I think that's just like a nice place to start. All right, so I want to keep the orbital radius constant. So think about what you need to do to the velocity to keep the radius constant. To keep the radius constant. All right, as I increase the mass. So I'm going to increase the mass of the sun. All right. So if I make the mass bigger, what do I have to do to velocity? I misspoke before. If I make the mass of the sun bigger, what do I need to do to the velocity to maintain that radius? Well, if I just let it run like this, I actually get in orbit, but notice how I'm not maintaining the radius. The radius shrunk quite a bit. Okay, though this is an ellipse, the radius of the ellipse, the semi-major axis, is significantly smaller. So we're going to reset that. Okay, or actually what I can do is I can pause it right at the top there. So think again, what do I need to do to this velocity to maintain that radius? Okay, well, if I make my mass get bigger to maintain my radius, let's see. If I increase the velocity, let's see if I can get that perfect circle again. Not bad. So I increased my velocity. I don't quite have the perfect circle though that I had before. So let me pause it right here again. I need to pull that down just a little bit. Now you'll see I pretty much have my perfect circle again. So when the mass of the sun went up, I needed a greater orbital velocity to maintain my 2-box radius orbit. So my orbit's the same radius as it was before. Notice how the mass of the sun was way bigger, the velocity is way bigger. We would expect that according to our equation. Look at your equations that we got last class and see why that's true. And you'll notice that if you get a perfect circle, the force of gravity vectors are always going to be the same length towards each other. So this isn't quite a perfect circle, but it's pretty good. Now, how does the mass of the planet affect the orbit? I think we discussed last class. It wouldn't. Notice how I can increase the mass of the planet, but it is not affecting the orbit whatsoever in any way. So this next one is changing mass and orbital period. Well, how does mass affect orbital period? You can actually not change the simulation at all. We still have our mass of the sun is 2. We know that the orbital radius of the Earth, when it was at the 2 box radius, or the orbital period of the Earth, when it had that 2 box radius for the orbit, was 365 days. So let's see if the period of the orbit is still 365 days. So I'm going to hit clear, and it resets it. So before it finishes, think to yourself, what would you expect here? Think about your period equation. R is not changing. You're just changing the mass of the sun, of the object that's at the middle. So think about how that's going to affect the orbital period. So the orbital period was significantly less. Now think about why that makes sense. If you look at the formula from last class for orbital period, as mass gets bigger, orbital period gets smaller if the orbital radius is held constant. The other reason this makes sense, and we discussed it last class, was that if something is going faster and the circle isn't getting any bigger, it's going to get around that circle faster. So the period would go down for that reason as well. So there you can talk about mass and orbital period. Here, radius and orbital velocity. So here I just want you to keep the masses what they are. Okay. So it says, how does the radius of the Earth's orbit affect its orbital velocity? Okay. So I want to keep the masses constant and I want to change the radii. I'm just going to reset this. So I'm going to change the orbital radius by making the radius for now, just make it smaller. So if I don't change the velocity at all, I'm going to crash into the Earth. So think to yourself, does it have to go faster or slower to get into a circular orbit? So what I want to do right now is I want you to do the same thing. I want you to bring this in here. Think about what you need to do to the velocity to get a perfectly circular orbit. Try to get a circular orbit with a radius of 1 box. So try to get a nice perfect circle right here. So just keep playing with the velocity, bigger or smaller, until you can get that. So again, you kept the masses constant now. You made the radius smaller. Think about how that would affect the orbital velocity you would need. Then with that, you can see how the radius affects orbital period. Okay, so you can make a comment about that. Okay, and compare it to your equations. And then for this last one here, this is a question for you to answer. It says Mars is 1.5 times as far away from the sun as the Earth is. A student claims that this means that Mars will have an orbital period of 547 days, which is just 1.5 times 365. Use your equations to show why this is wrong. Find the orbital period of Mars. And do not look it up until you answer the question. Okay, you can use factor of change to answer this one. I'll tell you that right now. Okay, so don't go looking at the mass of different objects and the radius, and you can use factor of change, and all the information right here is all you need to answer this question. All right. So even if you didn't have the worksheet for this, I should have said this at the beginning. You just do this on paper, just number everything. Should be pretty straightforward. All right, and hopefully I will see you guys tomorrow.